Okay, so we'll go over 11 through 15 on the 2014 multiple choice. So the first one says for 0 to 6, the graph of the derivative of f is piecewise linear as shown above. If f of 0 is 1, what's the maximum value of f on the interval? So if this is the graph of the derivative of f, we have to integrate this to answer questions about f. Right, so this is saying that when x was 0, f of 0 was 1. And so this is the change, the rate of change of f. So what we need to do is figure out how much does it change from 0 to wherever the maximum would occur. So on this section of the graph where we have positive y values or positive derivative values, these are the places where our function would be increasing. And it increases by this much area. Right? This area is how much the value increases by. Then it decreases where the y values are negative. So this negative area would be how much it would decrease by. And then it would increase it again a little bit. So the maximum is going to happen right here at 3. Because it starts off with a value of 1. And then it adds all of this value before it takes away all of this value. And then it adds back just a little bit of what it took away. So the most value that it will have will be at 3. So what we need to do is take the initial value of 1 and add this change in the value, which is the area of this triangle. So triangle with a base of 3 and a height of 2. So its area is 3. So we should get 4. So just remember, if you want to know the total change in something, which is basically what they're here, to find total change, you integrate the rate of change, which is what the derivative is. So if f of 0 was 1, then the maximum would happen at 3, and it would add this much value to the function. Does that kind of make sense? All right, number 12. Let f be the function given by f of x equals 9 to the x. If 4 subintervals of equal length are used, what's the value of a Wright-Riemann sum approximation for 0 to 2, the integral from 0 to 2 of f of x? So to go 4 subintervals, we would have to go 0 to 0.5, and then 0.5 to 1, 1 to 1.5, and 1.5 to 2. Each subinterval would have to be 0.5 wide. To make 4 subintervals from 0 to 2. So we're going to plug these values of the function to get the y values, and then we can calculate the Riemann sum, because remember the y values are going to be the heights of our rectangles. So if I plug 0 in, 9 to the 0 is 1. Anything to the 0 is 1. If I plug 0.5 in, that's 9 to the 1/2. Right, 9 to the 0.5, 9 to the 1/2. That means the square root of 9, which is 3. Then if I plug 1 in, I get 9. 1.5, that would be 9 to the 3/2, which means the square root of 9 cubed. Right, so that would be 27. And then 9 squared would be 81. Right. Basically, you're multiplying by each time here. Right. 1 times 3, 3 times 3, 9 times 3, 27 times 3. Okay, so now we can do the Wright-Riemann sum. So we're going to have 4 rectangles. Right. Each one of them will have a width of 0.5. And then we'll use the right height. So from 0 to 0.5, we would use 3. Then we'd use 9, 27, and 81. So 1.5 plus 4.5 plus 13.5 plus 40.5. There we go. So that would be 6, 19.5, 60. So see? Right? Yes. Right. Does that make sense? So you had to fit to yourself and just read stuff. Alright, so number 13 is the penal derivative problem. So let me do some just plain problem here now. So we're taking the derivative is the quote. Have to do motion. Have to do low behind minus I do over lower. So I'm going to simplify that out. Just reading this minus and the 2x. So minus 2x is minus 2x. So that is giving negative x squared minus 2x plus 1 over x plus 1 third. So see? I haven't talked about yet. We're going to about it, but I'll show you how to do it stuff. There's 3 things that are associated in motion. There's position, and then there's the rate of change of position, which is called velocity, and the rate of change of velocity, which is called acceleration. So velocity is the derivative of position, and acceleration is the derivative of velocity. So work way down position to velocity to acceleration, you take derivative. Which means to work way back up from acceleration to velocity or velocity to position, you integrate. Right. So just so you know, you start with what you're trying to get to determine whether you're going to get a derivative and a final integral. And this problem is tells velocity. So start with velocity. E of t is sine of t times t. If the problem is at 4, t0, what's position? So we're going from velocity to position, so we're integrating. So this right here is what we call the initial position. This is saying that at the starting time when t is 0, the particle was 4 on x-axis. And so we're basically going to do is calculate the change in its position by integrating the velocity. So we're going to integrate from 0 to pi over 2. I couldn't want to know what position when t is over 2. So we know what the position was when 0. That's where we're starting. We're going 0 to pi over 2 of sine of t. So in order for me to integrate this, I have to do u substitution. 2t is the sine. So 2t is going to be my u. And the derivative of that is 2. So I'm going to have to give myself 2 and balance it with 1 half. Here's 1 half. Because I did use substitute, I'm substituting u for t. And then 2 dt is du. That's the derivative of u. 2d serving du. So now I integrate sine. I get negative sine. I'll put my 2d back in for you. So this 4, because when I integrate sine, I get negative cosine. I'm going to make this minus 1 half cosine. I'm going to put my 2t back in my u. And we begin top number, we begin the bottom number, and we track. So, oh, yeah, that's okay. Make sure my order is right. Let's see. Do the cosine f. Okay, right, is that? So I put in pi over 2, I get negative 1 half cosine pi minus negative 1 half cosine 0. Yeah. So I'll keep it 4 separate. I would do myself because of 4 here. Really what I want to do is integrate, and then I'll add 4 at the end. So when I integrate, get negative 1 half cosine 2d. And so I put pi over 2 in, it gives cosine pi. Minus, and I'm going to put 0 in, so we need cosine 0. So cosine of pi is negative 1. So this is going to be 1 half. And the cosine of 0 is positive 1. So plus 1 half. So, make sure it's right. Yeah. So this the integration is kind of so we have this 4, so our initial position that starts with 0, and then to find how the position changes from 0 to over 2, we're going to integrate the velocity. So when I integrate it, I got cosine 2, negative 1 half cosine t. And so if I put pi over 2 and 0, do its part here. Negative 1 half cosine pi minus negative 1 half cosine 0. So that gives me cosine pi. Pi is here at negative 0 cosine x. 0 is over at 1 0 and cosine x. So the sine of pi is negative 1 times negative 1 half with 1 half. And cosine of 0 is 1, so 1 half times 1 half. Oh, one more. Okay, the function gx is differentiable and increasing for all real numbers. So what that tells me is decreasing means that the derivative of g is always positive. All right. That's what f of g is increasing means. And differentiable means that derivative exists. So I can find the derivative of g, and the derivative is always positive because it's increasing. So what interval is the function y equals g of sq minus 6x increasing? So now we're in a composite function with g on the outside and its new function on the inside. To figure that's increasing, we need to look at its derivative. Figure out where the derivative of the function is positive. So where this function is increasing. Take the derivative, we have to the channel. We do have a positive g on the outside, so we have to take the derivative of g, leave inside, times the derivative of the inside. Alright, so derivative of the inside would be cx minus 2x. So we know since the derivative of g is always positive, this part will always be positive. This part is the derivative of g. So the question is really more about this. So I'm going to factor this to find the critical orders. So this be 0 and 4. Move 0 and 4 in that. We through that, let those go through. So I know what again this part is going to be positive. The question is, what's going to happen when I plug e? So I plug -1, that would be -3 and -5, positive, negative, positive. If I plug in 1, I get +3 and -3, positive, negative. And if I plug in 5, -15, +1, so positive, positive. So this is increasing, negative infinity 0, and from 4 to infinity. So it'll be a. Makes sense when we did increase when we had to do that. Okay. The nice about response questions is that they have some questions that they tend to ask every year. This is one of those. I'll show you some of the other props that are similar to this one. So this is the graph of the derivative of f. So this figure above is the graph of f prime or derivative of f of a exponential function f on the interval 3, 4. The graph of f prime has horizontal tangent negative, so letting you know the derivative of this graph is 0 here at 1 and 3. So just basically letting you know where this graph has min maxes. The areas of the regions bounded the x-axis and the graph derivative, the intervals -2 to 1 and 1 to 4 are non-12. So they're in the area of this little region and non-area of this little region itself. And all x coordinates at f has relative maximum here. So remember, this is a graph of the derivative f. They're not asking you what this has maximum. They're asking you the integral with maximum. Where the function. This is the derivative of maximum. Remember, your function has a relative maximum anywhere the derivative 0 are defined and changes from positive to negative. The definition of relative maximum. Relative max happens whenever the derivative is 0 or defined and changes from positive to negative. We only have that at one place on the graph. There's only one place where the graph is either 0 and defined and the second on 0 at -2 and 4. And only one of those where it changes from positive to negative at -2. So our A here, you would say f equals -2 because the derivative is 0 and changes from positive to negative. So let's look at how this would work. Hold on a second. So each free response question is 9 points and is partial credit given. Let's look at this. Look, and so don't know what stage 12. This work a little bit. Okay, here we go. Here are the sorting line of this. So we're part of this first point. So this says that they do the same thing. So derivative 0, -2, 1, and 4. The derivative changes positive to negative at -2, so therefore it's relative maximum. You have to have worded exactly like this. You get 1 point for figuring out that at -2 and 1 point for giving your reason. So we've got those points apart. Alright. Alright, so part B, on what open intervals pain in -to 4 is the graph goes into down and decreasing. So one case on here with the second derivative be negative, decreasing is where the derivative be negative. That's how you want to look at the graph here with the second derivative. Remember, if this is the graph of derivatives, the second derivative is the derivative of this